Okay. Let's begin. I think our friends in Stockholm are not with us today, but they will have access to the recorded version of this. So you should ask twice as many questions because you have to make up for the absence of the students at KTH. I know you've all completed homework number 6, but do you have any questions about it before we begin our discussion today? Today we're going to start talking about, well, we did a little bit of that last time, but we're going to get into a serious, detailed discussion of classical unsteady aerodynamics. That's chapter 4 in the book for those of you who are reading the book, which I hope is all of you. All right, several times. If you read it more than once, we do not charge you more. I mean, you can read as many times as you like. It's the same rate. But any questions about homework number 6 before we begin? That means they must have total. There are 2 possibilities. I won't ask for a show of hands. One possibility is they have total command of the homework. The other possibility is they haven't even started to think about it. I'm not going to ask you which one that is. Okay, so we're going to talk about unsteady aerodynamics. Unsteady aerodynamics. Now, I'm even going to say the classical theory, which is a theory that is still used today by the aerospace companies and even by those of us who do research under appropriate circumstances, most of the time. But what I mean by classical theory is we're going to use potential flow theory. The equations of fluid mechanics come in several different flavors. The classical theory assumes that there's a potential flow. What does that mean? That means there's a velocity potential, almost invariably denoted by phi, which in general will be a function of x, y, and z, because the fluid exists in 3 dimensions, right? Beams exist in 1 dimension, plates exist in 2 dimensions. The fluid in this room exists in 3 dimensions, although sometimes, as we'll see, we can ignore one of the spatial dimensions when we do the aerodynamics. But in general, fluids are 3-dimensional fields. And the reason we call it a velocity potential is because if we take the gradient of this potential, like all good potentials, we get something. In this case, we get the velocity. That's why it's called the velocity potential. So the gradient of phi gives you the vector velocity of the fluid at a point x, y, z at time t, right? That's what it does. So we need to be able to write down an equation which governs the velocity potential in solids. Well, that equation was determined a long time ago. And there's a wonderful derivation in chapter 4, which I do not plan to go through. But I'm going to let you read it because I could regurgitate what's in chapter 4, but it only takes about 5 pages or so. And I'm going to let you read it. Now, let me ask you one question. How many people took Professor Bliss's course in acoustics? Well, you already know what the equation is. It's the same equation as in acoustics within the classical framework. How many people took a course in PDEs? And what are the 3 great equations you always discuss in a PDE course? They are wave equation. That's ours. What else? Heat equation. We'll sort of get to that. And the third one is, which is actually a special case of the wave equation, sort of. Okay. So acoustics. We're going to start with acoustics. because classical unsteady dynamics is more or less acoustics, but with a little twist that makes it more interesting. The classical equation for acoustics is the wave equation. It's the Laplacian operator acting on phi minus 1 over the speed of sound squared. That's the speed at which waves are propagated in the fluid, times the second derivative of phi with respect to time. That's the wave equation. Okay. Or if I write this out in somewhat fuller form, it's this. A lot of second derivatives, right? Thank you. Okay, so we'll call this equation 1. And all we need to do is solve that equation. The general solution of that equation is known analytically. Has been known for a very long time. It's not particularly useful because not only must we satisfy this difference equation, we also must satisfy some boundary conditions. And that's the hard part. It's not solving this equation. After all, it's the wave equation. How hard can that be? But the boundary conditions prove to be quite challenging, even within the classical theory. All right. And what are the boundary conditions, therefore, you might ask? Well, one is that if I have an airfoil on a flow and I go way far away from it, way far away, you might think that nothing much happens there. Well, that's sort of true. Things do tend to die off as you head towards infinity, but in some cases the waves propagate out, and according to the classical theory, they don't dissipate because we left out viscosity, right? And so then we have to distinguish between waves going out and waves going in, and based on physical reasoning, ad hoc physical reasoning, we say, well, the waves must start at the airfoil. That's the only thing that's disturbing the fluid, and they must go out. There aren't any airfoils out in infinity unless someone's out there doing something or come back in. We assume there's no one out there. Okay. All right. So remember what the velocity potential is. I take the gradient of the velocity potential, I get a velocity component. More particularly, if I take the derivative of phi with respect to z, and I'm thinking of an airfoil like so. I'm going to make it a very thin airfoil, so thin it's only a straight line. And here I have a flow with a velocity infinity, and I have a coordinate system where x is in this direction, z is in this direction, and y is in the board. I need to say that the velocity component in this direction is basically equal to the velocity component created by this body. Okay. And so if that body is moving up and down with a displacement w, that's a good thing. Yeah. For the w. Then this velocity, which is the velocity of the fluid, evaluate on the surface. That's z equals w. W describes the deflection of this surface. Must be equal to dw dt. That's the velocity of the surface, right? Well, we neglected a couple of things. First of all, there's really might be some motion in this direction too, but most of the motion is in this direction. So that may be a bit of an approximation. But the biggest approximation is we replace that by 0 usually. Why? Because it simplifies the mathematics. That's why we always make approximations, to simplify the mathematics. We don't just do it because we like approximations. And so we could try to make this boundary condition apply to the actual deflected position, but that makes the problem harder, a lot harder as it turns out. And if you don't believe me, when we solve some of these problems, you try to do it with that boundary condition instead of z equals 0, and you'll see you run into some difficulty. Okay. Then, so I'm going to call this equation 2. Then, it's nice to find the velocity potential, but I'm an aeroelastician. I want to know what the pressure is. All right? And so, fortunately for us, Bernoulli, a long time ago, I've forgotten which Bernoulli was. There were 3 of them, right? There was a father and 2 sons. But one of the Bernoullis constructed the following relation. He said the pressure, this is actually the perturbation pressure. In fact, I probably should put hats on all of this to indicate we're talking about small motions and small disturbances in the fluid and all that. The perturbation pressure, this is the pressure change due to the motion of this object in the flow, right? I mean, there's some mean pressure, which is usually called P sub infinity, right? That's 14.7 psi in this room. But then when I speak, I'm moving my tongue. That's a vibrating object, which is creating pressure fluctuations in the air, which is propagating into your ear, and you have a membrane, the basilar membrane inside your ear, which oscillates in response to my voice, which creates this pressure, and that in turn is connected to some neurons and goes through an electrical path to your brain, and you perceive that you hear me. Isn't that a good thing? So we're doing that problem too. Anyway, this is the perturbation pressure, and it's equal to minus, to a classical linear approximation, minus the density of the flow, the mean density, this is not the perturbation, the mean density, times d phi hat dt. This is a form of Bernoulli's equation. Now, where did that equation come from? Well, I could say Bernoulli said it was so, and he's a great person, or was. He's no longer with us, unfortunately, so we can't ask him about it. But a lot of people since over the last 100+ years, probably closer to 200 years, have assumed this is correct. I'll show you a word. It can be rationalized, but not derived. Okay, but this is it. We have this boundary condition, we have 1 in infinity, and we can use that to solve for phi, and once we have phi, we compute p, and we're done, right, more or less. And if you do this when the Mach number is sufficiently high, you get piston pairs, okay, which is what you're using in your home. If the Mach number is lower, you get something a little more complicated. But we are going to start with what I'll call the easier case. We're going to do supersonic flow first. And then we're going to back down to subsonic flow. And then we're going to go back up to transonic flow. Because that's the order of difficulty. It's not the order in which the work was done historically. It's the order of difficulty. Supersonic turns out to be easier. So we're going to do that case first. Now, you may have been thinking, first of all, those of you who took the course in acoustics, did I get that right? Is that true? Is that what you learned in acoustics?
Yeah, that was the whole course, actually.
I've just covered the whole course ever. Well, we move fast in this course. Leave out some of the details. Okay, but us aerodynamics is more than acoustics, right? And what have we left out? Well, we've left out the fact that there's a mean velocity. In acoustics, you usually ignore that. There's no mean velocity. I mean, I could bring in a fan and create a mean velocity, right? But as we sit here, this air, until I start speaking, is sitting here, right? But in aerodynamics, we have to take into account the mean velocity, which is very important, because it turns out that when the mean velocity u infinity is greater than the speed of sound, this truly is a wave-like equation. But when it's less than the speed of sound, it becomes more like Laplace's equation, more or less. And then right near Mach 1, the whole theory, this whole classical theory breaks down, And if you go to the next approximation, you get something that looks a lot like sort of the heat equation. So unsteady aerodynamics has all those classical equations buried in it if you pay attention. Okay, now this equation is valid in a certain coordinate system. It describes what I'm in the fluid, but only if I'm up on a cloud, fixed with respect to the fluid, and I'm watching the airplane go by at a velocity u infinity. But I don't want to be in that coordinate system because I've got to apply a boundary condition on the vehicle. So in order to apply the boundary condition, I want to be in that coordinate system, which is going to make this equation, it's going to add some terms. So let me tell you what they are, and then I'll show you where it comes from. Okay, first of all, because I really want to be in the vehicle fixed coordinate system rather than the fluid fixed coordinate system, I'm going to put a prime on all of these. All x, y, z, and t. Why? Because I'm now going to use x, y, z, and t for the vehicle fixed coordinate system, and that's the coordinate system I want to be in. And when I get there, I don't have to be carrying along all those primes. But I do want to distinguish between the fluid fixed coordinate system and the what is usually called the body or the vehicle fixed coordinate system. Okay, so that's page 1. Moving right along, page 2. Page 2. It turns out if we are in the vehicle, in the body fixed coordinate system, then 1 becomes, I'll put a B over here for body, right? Remember, it was the wave equation before, right? Well, del phi is, that's decided there. Okay, it's still there. And then I have minus 1 over a squared infinity. And then I had the second partial respect to time, right? Well, what I have now is I have the partial respect to time. Now, this t is not t prime. I'm now in the body fixed coordinate system, and I have a clock in that system too, right? So I'm the body fixed time, if you will. Plus u infinity, partial with respect to x. And I'm going to write that as squared. Phi equals 0. And let me explain what this notation means. But I write it this way for a reason, as you'll see. When I do this, what I mean is, well, I mean more or less what you might think I mean. This is an operator. This is a derivative operator, right? And I take that derivative operator and I apply it twice to something, right? Like phi, for example. Right? And if I do that and I work it out in detail, it's the second derivative of phi with respect to t plus 2 u infinity, second derivative once with respect to t, once with respect to x, plus u infinity squared, second derivative with respect to x. That's what it is. So this notation just is a compact way of saying that. So what's happened, you see, whereas before in the fluid fixed coordinate system I only had that, now I have these extra terms. Now I have these extra. So, and that's equation 1. Equation 2, that was the one that said d phi dz approximately on z equals 0. It was, it was dw dt. Well, now it's d dt plus u infinity d dx operating on w. So note that if I'm in the body fixed coordinate system, even if w does not change with the time, there's still there's still a term there, right? So even in steady flow, if I'm in the body fixed coordinates, there's some non-trivial contribution to the boundary condition, which is really important. Otherwise, steady flow aerodynamics would be pretty trivial. Right? And then finally, the perturbation pressure. And again, I should put other fees on all of it. I'm going to eventually drop all these hats because I get tired of writing them, right? Again, we're talking about perturbations. And it's important to recognize this is the perturbation pressure, not the total pressure in the air. This was, before, it was minus rho infinity times ddt of the velocity potential. But you'll not be surprised by this time, I hope, that it's that plus u infinity ddx of the velocity potential, which means that even if this doesn't change with time, there's still a non-trivial contribution to the perturbation pressure once I sit in the body fixed coordinate system and recognize what's going on. Okay, so the question is, where does this operator come from? And it comes from making a coordinate transformation from the prime system, the fluid fix, to the unprime system, the body fix. So we need to make it. We need to make a coordinate transformation. This is a great question for a final exam, qualifying exam. So pay close attention if you think you're going to take a final exam or a qualifying exam. Okay. All right. So let's look at the following. First of all, I'll draw myself a nice airfoil. Okay. And up here in the cloud, up here on the cloud's up here someplace. I have Z prime and I have X prime. And there's a Y prime too. And I'll initially think of starting my clock at time 0, right? And then down here, I have X, Y, and Z at time t equals 0. Okay? And the person on the airfoil and the person on the cloud have agreed to start their clocks at the same time. And they've agreed that the speed at which the airfoil is moving is way less than the speed of light. So we're going to ignore relativity effects, right? You know, the airplane at most is going to maybe 1,000 meters per second. Speed of light is 86,000 miles per. I forgot. It's big, right? So u over the speed of light is small. We are making that approximation, but I hope you'll work with me on that. Maybe that's okay. So the fact that we're not. Okay. Also, we're going to let Z and Z prime be aligned. Why not? They're both up, right? And the same thing for Y and Y prime. But of course, it makes a difference with respect to X and X prime, right? Because one's stationary with respect to the fluid and the other one's moving with the velocity. So let's write down the following. X prime, well, first of all, we will do this. At time t equals t prime equals 0, but only at that time, we're going to start off so that X and X prime are both 0. Everything's lined up at time t equals 0, and then the airplane begins to move. Okay. So now, when X equals 0, that means I'm always at the leading edge of the airplane, right? So if I look at that point, X is always 0, but X prime is not. X prime keeps getting more and more negative. So at X equals 0, X prime equals minus U infinity T or T prime. It doesn't matter. They're both the same, right? Okay. But also, as we discussed before, at T equals T prime equals 0, X prime equals X. but it also equals 0, of course. So it's easy to see that x prime, I hope, is equal to x, right, minus u infinity t. And if you don't want to look at it that way, you can kind of look at it the other way. Okay. So this is a key equation. This tells me how the x prime and x are related. And that's what I need to convert the fluid fixed coordinate system equation into the body fixed. So let's do that. Let's make me write this down again. So where are we again? We're starting out in the. I'll put a prime here to note I'm talking about fluid fixed. And again, I'm leaving off the perturbation hat. I hope you'll work with me on that. And just to be a little more explicit again. Well, y prime, z prime, and t prime are all the same as y, z, and t, right? So I know this. Well, I got to be a little bit careful here. No. Be a little careful here. Sorry about that. Those are the same. But I'm going to have to worry a little bit about these others. So let's do the following. If I have partial of v with respect to x prime squared, it's the partial with respect to x prime of the partial of phi with respect to x prime. You'll agree with that, I hope. So let me do this part first, and then I'll do it again after that. So partial phi with respect to x prime is equal to what? Well, it's the partial of phi with respect to x times the partial x prime with respect to x, plus the partial of phi with respect to y times the partial y with respect to x. Oops. Got this upside down, sorry about that. X with respect to x prime. Partial phi with respect to y, partial y with respect to x prime, and so forth. But, okay. 1. And 4 was what? 4 was x prime, x, t. And I can rearrange this so that x is x prime plus u infinity t, which is also x prime plus u infinity t prime. Right? So, what do we have? And t, of course, is t prime. You don't get anything but many of these. And from this one, partial x with respect to x prime is 1. Right? So partial phi with respect to x prime is the same as partial phi with respect to x. And therefore, the second derivative is also. Okay? So what have we concluded at this point? This, and this don't really change. Well, hopefully something changed with this one. If it doesn't, we're going to say acoustics and unsteady energy or something. So let's do the other one. But let's look at partial phi with respect to t prime twice. What's that equal to? Okay. So we'll first of all do partial phi with respect to t prime. It's the partial phi with respect to t times the partial t with respect to t prime plus the partial phi with respect to x times the partial x with respect to t prime plus some other things which turn out to be 0, and I'll let you verify that. Partial t with respect to t prime is clearly 1, right? And what's partial x with respect to t prime? Partial x with respect to t prime is u infinity. So this is u infinity times d phi dx. And if we do it again, we get the same factor, the same operator acting twice, which gives us our desired equation. Okay. Now this kind of thing has been known for a long time. In fact, this predates Newton. It is said. I don't know. I haven't looked up this for myself, but it's named after Galileo. So it tells you it's been around a while, right? Because this is usually called a Galilean transformation. I've also seen it called the Newtonian transformation. I think Newton probably actually had a deeper understanding of this than Galileo did. So, at least in the English literature, Galileo gets credit. So whether it's Newton or Galileo, it's one of those famous people. All right. Okay. So what have we done? We've traded the simplicity of the field equation for a more complicated field equation in turn to get a easier way of applying the boundary condition, because now we're in the body fixed boundary condition and we know where the boundary is. We're in that coordinate system, right? Otherwise we'd have to keep chasing. If we're in the fluid fixed system, we'd have to keep chasing the body to apply the boundary condition, which is not a good idea. Okay. Now, so let's look at that equation a little bit more then. Now we have del phi minus 1 over a infinity squared. And I'll write this out in its full glory now. Oh, sorry about that. Okay, but before we actually solve a problem, let's look at this a little bit. We're going to do unsteady dynamics. So every time we solve a problem, it also covers steady aerodynamics. It's a special case, right? That is, if nothing's changing with respect to time, we can note that in our unsteady solution. Or if you prefer, if I take phi, which is a function of x, y, and z, and t, and assume it's some function yet to be determined of x, y, z times e I omega t, if I solve that problem and then I set omega equal to 0, I get the steady flow solution, right? And by the way, note that this classical theory is linear. The wave equation is linear, the boundary condition is linear, because we set z to 0, and that really helped. Actually, if we really prescribe the motion, ultimately we want to know how the fluid and the motion interact. We don't really know as an aeroelastician what the motion is until we solve the problem. But if you take the point of view of the aerodynamicist, if you tell me what W is, you tell me what the body motion is, well, I could in principle apply the boundary condition of the body too. Not if I really want to know the interaction, that's a harder thing. Anyway, if I set omega to 0, I get the steady flow solution. So that corresponds to all these time derivatives being 0. So what do we have then? We have del squared. Well, let me write down. Let's now look at special cases steady flow. Steady flow means the body is not oscillating, so the fluid is not oscillating, it's not changing with time, right? Then I just have del squared C minus 1 over A infinity squared times U infinity squared. This is the only term that survives, right? But then, if I rearrange this, remember there's a second derivative with respect to x over here too. So I've got 1 minus this ratio, which always appears in a prominent place, so I'm going to give it a special name. I'm going to call it the Mach number. Sorry about that. Mach number. So I've got a term that's 1 times the second with respect to x, right? Minus the Mach number squared. I'm rewriting it this way with malice aforethought. Let's see, I give these equations some numbers, and maybe use the same numbers I used before. Well, I guess these are new numbers, right? So last equation number I used was 4, so this will be 5. And now this will be 5 with an S for steady flow, I guess. Well, this equation, even though it's steady flow and nothing's changing with time, still has some interesting properties. In particular, note that this coefficient changes sign depending on whether the Mach number is greater than or less than 1. If the Mach number is less than 1, then this coefficient is positive. And this is really more or less Laplace's equation. In fact, what you can do is you can rescale x. You can define a new variable which is scaled by this coefficient. So this reduces to Laplace's equation, provided the Mach number is less than 1. And there's a famous scaling law due to Prandtl and Glauert that tells you how it goes. On the other hand, if the Mach number is greater than 1, the sign of this term is negative. This really is a wave-like equation in space. So for supersonic flow, it is a wave-like equation, but it's wave-like in space rather than wave-like in time. And if the Mach number happens to be exactly 1, this term goes away. Is that okay? Well, in a way. So let me point out the key. If this is less than 1, then essentially Laplace's equation with a rescaling of x. I thought about that. Yeah. And what would the scaling be? Well, since it's a second derivative, you take the square root of this, right? And define a new variable, which is x over the square root of this, and then you can make this go away, right? And as long as it's a positive number, that's fine. And then you just solve the problem as you would any other problem in that space, and then remember you rescaled them. And what that tells you is that how, if you have the solution for m equals 0, you can get the solution for any other m greater than 0 but less than 1 by doing that rescaling. If it's greater than 1, then of course you have a wave equation, but it's a wave equation in space rather than time. And if the Mach number is exactly equal to 1, it depends. But you can see something interesting from this equation. If you set the Mach number as this term goes away. Okay. Believe it or not, you get something sensible if both of these terms survive. But that means I have to be in a 3-dimensional flow, right? I can't be in a 2-dimensional flow. I can't be in, what do I mean by 3-dimensional? Well, let me draw a picture on here. I'll look down on, here's the x direction, here's the y direction, the z is coming out of the board, right? And so if I have a flow velocity u infinity, and I have a delta wing like this, then then this is definitely three-dimensional. It's not only Z, but things are happening in Y and X and so forth. On the other hand, if I have a very high aspect ratio wing, like a Boeing or Airbus transport, so the wing goes way out here, right? So the flow is almost two-dimensional over many of the sections because the span is so large. Then this term doesn't become very important except at the tips. And then if I'm at Mach 1, this term isn't very important. This term goes away, and this whole theory breaks down. But if I have a delta-like wing, it still gives you a sensible answer. Maybe not a perfect answer, but a simple answer. And so at Mach 1, you have this. By the way, you still have, what else? You still have the same boundary condition, right? I won't bother writing again. And you still have the same expression for perturbation pressure. And so phi still depends on X, as well as Y and Z. And the dependence on X is given through the boundary condition and through Bernoulli's equation. But the field equation is basically, if you look at it, that's Laplace's equation in the YZ plane. So basically, the PDE in 3 dimensions is reduced to a PDE in 2 dimensions. And so at each X, you solve this Laplace equation, and you get phi. And this is called slender body theory or slender wing theory. And it was very controversial for a long time because people thought that, gee, that can't be right. But a couple of very smart people proved it was. One was Max Monk. And the other was R.T. Jones. And there are other people who worked on this over the years. So if you have a very low aspect ratio wing, you have something where the span is small compared to the chord, this actually gives you fairly sensible results. What it also tells you is that for these low aspect ratio wings, if you look at it, the lift and the pressure distribution doesn't change much with Mach number, up to a Mach number like maybe 3 or 4. So the pressure distribution in 0 and 1 and 2 is all about the same for very low aspect ratio wings. It's kind of interesting. Okay. On the other hand, if you try to solve a 2-dimensional flow problem, which means you're going to throw that term away, and then I set the Mach number equal to 1, all I have left is this, and that's too severe. I mean, that just gives you nothing at all of interest or accuracy. Okay. Now, what about if you have unsteady flow and you still have a finite frequency and these other terms still appear? Well, what happens in general is that you have both waves. You have waves in time in both subsonic and supersonic and transonic flow. Okay. So things get a little more complicated there. Okay. With that, let's see. Yeah, we have time. So we're going to solve I'm going to stop here unless you have some further questions. We're now going to solve a 2-dimensional, unsteady, supersonic problem. Okay. And of course, we'll get the steady flow solution for supersonic flow as a side benefit. Are we ready to do that? We are. What have I said so far that's confusing to you? Anything? You think you understand it?
I'm slightly confused by the sensible answer to the delta wing.
Say again.
I'm slightly confused by how you get the sensible answer to the delta wing.
Oh, why you do that? Well, it's not obvious. And as I mentioned, it was controversial for a long time. People solved the problem and said, that can't be right. And then finally, I mean, it took Monk worked back in the 1920s. He worked on airships. Okay. He developed, dirigibles, balloons, things like that. And the experiments and experimental capability at that time was not great. And so when they made measurements, the measurements had a lot of uncertainty, and people weren't sure they got the right answer. Also, in a dirigible, it's a big, bluff body. It's low aspect ratio, if you think about it. But then the flow separates beyond the midpoint of the section, and therefore, for viscosity reasons, this theory is not great, right? But nevertheless, Monk kept persisting, saying, well, okay, it works pretty well until about halfway back on the dirigible, and then things fall apart. But it's not because this isn't okay per se. It's because I left out viscosity. It's not a failure of the potential flow theory as such. But it was only when people actually built low aspect ratio wings where the flow separation is much less of an issue. And they went to the wind tunnel and made measurements and compared it to this slender body theory. They said, oh, that's pretty good. Yeah. What else can I tell you about that? There's the way you correct this theory in transonic flow in the Monk number 1 is you actually add in a term that's, well, since you raised that question. This is a preview of the image. And let's just look at this equation again for steady flow. So let's talk about transonic flow for a moment. We have 1 minus Mach number squared. And this is the free stream Mach number, right? This is the mean velocity of flow over the speed of sound. And then we have these other terms. And I'm just going to do steady flow because it turns out, in a way, it's kind of interesting. This basic theory breaks down more readily in steady flow than it does in unsteady flow. If you are thinking of the body oscillating with a certain frequency, if the frequency is very high, then some of the difficulties associated with the transition from subsonic to supersonic through the transonic regime actually go away, or are less prominent. Okay, you don't know that, but for the moment, take my word for it. So the steady flow case is the hard case in that sense. All that happens in transonic flow, if you want to improve on this theory, is you replace M sub infinity by the local Mach number. What do I mean by that? Well, the true flow field is not just U infinity, it's U infinity plus a perturbation. It's U infinity plus d phi dx, right? It's d phi dy in that direction and d phi dz in that direction. So these are the fluid velocity components. And essentially what we're doing is we're neglecting that term as far as this term is concerned compared to that. Okay. Yeah. We're also neglecting the fact that A infinity, the speed of sound, also has a perturbation component. Okay. And so what happens is that in transonic flow, you really want to replace M infinity by M local, where M local by definition is U infinity plus d phi d hat, I'm leaving off the hats, d phi dx over A infinity plus A hat. Okay? And if you think about this alone, if I do that, that alone makes this linear PDE a nonlinear PDE. Right? Okay. But if this term is small, even if, say, the local Mach number is, what might vary from throughout the flow field over the wing, it might vary from, if the free stream Mach was 1, the local Mach number might go from 0.9 to 105 or something, right? It's still pretty close to 1. So this term is still pretty small. And therefore, when the free stream Mach number is near 1, these two terms dominate, we're still in billions. Does that help? A little bit, not much, a little bit. But on the other hand, if you have a very high aspect ratio wing, so that term is not prominent, then you need to, near Mach 1, even though this term is small, it may still be bigger than that term, and you need to do something about that. Okay. All right, other questions before we solve a problem here? Other questions, comments? Okay. So we're going to do supersonic two-dimensional. That means we're going to ignore derivatives with respect to y, right? But unsteady flow. So what do we have? We have, well, we had what we had before. We have this plus this. Oh, not y. Sorry about that. I think I wrote this. Actually, I think I wrote this right there. We're going to ignore derivatives with respect to y, right? So I'm thinking of an airfoil and wind tunnel which spans the complete wind tunnel, and the flow is all aligned, so it's like a 2D flow all the way along. Or I'm thinking of a very high aspect ratio wing where except that right at the tip, the flow is nearly two-dimensional. Things are not changing much with respect to y. And then, of course, I have these other terms. And now I'm going to do some more notation just to save myself from writing. Capital D dt is this operator. And this is sometimes called the substantial. It's really called the substantial time derivative, but people usually forget to say time. Substantial time derivative. Okay. We're going to look at simple harmonic motion. Why are we doing that? Well, actually, for a couple of reasons. Sorry about that. Simple harmonic motion. So we're going to assume that phi is now only a function of x and z. We've left out y in time. It's some function of x and z, which we are seeking to find, e, I, omega t. We're doing simple harmonic motion because early in the class we said, hey, if I have a linear dynamical system and I can do the simple harmonic motion case, then I can use that to construct the periodic motion case, right, by using a Fourier series. And then I can go from there to a Fourier transform and do the arbitrary time dependence, right? I can get transfer functions. There are aerodynamic transfer functions just like there were structural transfer functions and other aeroelastic transfer functions. So that's one reason. The other reason is if you're interested in doing a flutter solution and you only want to know the flutter point, in that case, at the flutter point, the complex part of omega is zero by definition, and I'm back to this case. That's another reason for doing this. If I'm doing gust response, and I know the transfer function, both the aerodynamic transfer function and the structural transfer function, then I can construct an aeroelastic transfer function and do gust response by saying power spectrum times the square of the transfer function. Power spectrum of the gust times the square of the transfer function equals the output transfer function. And of course, the other reason is it's going to be easier to do the mathematics for the simple harmonic motion case, right, than for a more general case, at least initially. But my point is that may be enough. Once I do simple harmonic motion, I can, if I persist, do arbitrary time to motion, and including random motion. But it may be enough for many applications. Okay, if I do that, then I'll reduce this PD to a PD only in X and Z, right? Because DDT will now be just I omega plus U infinity ddx, right? The I omega coming from a time derivative for simple harmonic motion. Okay. And then the question is what to do next. And what to do next, historically, is a fairly complicated story, which I'm not going to tell you. I'm going to tell you a simpler way. I'm going to take a transform with respect to x. I mean, you've learned about transforms, right? Here's a chance to learn, to use something you've learned. And the two obvious things to do are a Fourier transform, or in this case, we can actually use a Laplace transform. And how many people know that a Laplace transform is a special case of a Fourier transform? You people still know that? Okay, good. But Laplace transforms are sometimes easier to use, particularly if someone has worked out the inverse Laplace transform, which they have in this case. So we're going to take a Laplace transform with respect to x. But to justify the Laplace transform with respect to x, we have to make sure that nothing is happening for x less than 0, which it isn't in supersonic flow. But in subsonic flow, it is. So in subsonic flow, we're going to have to go back and use a Fourier transform, which is a little more complicated. So here's the idea. We're going to take a Laplace transform with respect to x. With respect to x. And so let's spend a few moments justifying that. Here we are with my body fixed coordinates. Here's x, z, and of course we don't have the y in this case since we're doing 2D flow. I claim that phi is 0 for x less than 0. Remember what x less than 0 is. That's everywhere ahead of the airfoil. The flow field doesn't know the airfoil is coming until it gets there in supersonic flow. And why is that? Well, think about it in terms of the fluid fixed coordinate system. If I'm up here on the cloud, the nature of the wave equation is the disturbances propagate in all directions from a point in the fluid with a velocity equal to the speed of sound, the speed of pressure propagation. So it goes that way with A infinity. It goes this way with A infinity. It goes up with A infinity. And it goes down with A infinity. Right? But we need to be primarily concerned with these two, and more particularly with this one. But these propagations are in the fluid fixed coordinate system. So when this thing moves through the air and increases disturbance in the flow, it propagates forward with the speed A infinity. But in supersonic flow, U infinity is greater than A infinity, so the airfoil is moving faster than the disturbance in the fluid. Okay, so it's only after the airfoil passes that you know it's been there. So more particularly, the propagation forward is this. Propagation forward in the minus x direction, if you will. And of course, it's this in the backward direction, if you will. And yes, even in the body fixed coordinate system, this propagation speed is perceived to be faster, right? And this one is slower, but it's still positive, right? So we're okay. You can also see another way in which transonic flow may become more complicated. What happens, of course, in transonic flow is this term becomes smaller and smaller until right at Mach 1 it goes to 0. So what I'm doing is when I'm flying through the air, I'm disturbing the fluid, and when I get close to Mach 1, those disturbances sort of build up on the airflow, right? They can't get away. In fact, what they do is they create a shock wave. And in the framework of potential flow theory, you can model shock waves. There's a debate about how well you model, but you can create shock waves even in a potential flow model. But that's part of the transonic story, largely. There are also shocks, if they're very weak shocks typically in this model, in supersonic flow, okay? But they'll come out naturally from our solution. Okay. So, because of this, nothing's happening ahead of the airflow. So, nothing's happening for x less than 0. So, taking the Laplace transform with respect to x is an okay thing to do. I hope you agree with that. So, let's do that. So, we're going to take a Laplace transform of phi bar. Remember, phi is phi bar EIMAT. And I'm going to call that capital phi because that's what I call it in the book. It'll be easier for you to read the book when I do that. And so what do I mean by taking a Laplace transform? I take phi bar, a function of x and z. When I assume EIMAT, all the EIMATs cancel out, right? So I'm going to take a Laplace transform of that. The Laplace transform, by definition, capital Phi, is equal to this times e to the minus px dx, right? This is Laplace transform. If I were a Fourier transform, I would replace p by I alpha, where alpha is a Fourier transform variable. And then if you work out the consequence, the inverse transform is the following. Phi bar is equal to 1 over 2 pi I, the integral from minus infinity, minus I infinity, plus I infinity, of capital Phi e to the plus px dp. Okay? And if you let p equal I alpha, you can show this reduces to a Fourier transform. Now, the hard part, once we do this, then we're going to reduce our differential equation in x and z, partial differential equation, to an ordinary differential equation only in z. We're going to be able to solve that analytically and find an analytical expression for capital Phi. Then all we need to do is put in here and perform this interval. You'll be happy to know that you can look that answer up in a book. I mean, there are books on Laplace and Fourier transform, right? And this happens to be one of the ones that's been worked out. You'll be thrilled to know that, right? Okay, so with this, let's see, I'm going to make sure. Yeah. Okay, so I'm going to call this 6 and call it 7. So now, when I take a Laplace transform, I have to also take Laplace transforms of terms like this, right? Now, the Laplace transform of that is equal to what? Based on your vast knowledge of transform theory.
P squared.
P squared. I like P squared. Times the Laplace transform of phi itself. Actually, in general, there's some tail terms, not quite like tail terms in Hamilton's principle, but they're terms involving phi bar at x equals 0. Actually, in this case, it's secondary, so there'd be a term involving phi bar and a term involving d phi bar dx at x equals 0. But we agreed that nothing's happening at x equals 0, or if you prefer, I'll do it at x equals 0 minus to make sure nothing's happening there, right? So I don't have those terms. Okay. So now, if I go back to my differential equation, ddt plus u infinity ddx squared phi equals 0. And now I assume that phi equals phi bar e I omega t. So every time I see a dt, I replace it by I omega. And I take a Laplace transform of the entire equation. So every time I see a derivative with respect to x, I have a p, right? then transformed we have P squared capital Phi, that's from this term, plus it's now, I'm going to write it as an ordinary derivative because all there is going away except the ones with respect to Z. Minus 1 over A squared infinity, I omega, because of the time derivative, plus U infinity times P, because of the X derivative, squared capital Phi equals 0. How am I doing? Okay. Why did I do all this? Well, I've now reduced this to an ordinary derivative equation only in Z, right? And it's constant coefficient. Now, it's true that one of the coefficients involves the frequency, but you tell me the frequency and it's a number. It also involves the Laplace Transform variable, right? Well, it should, because eventually I'm going to have to do the inverse transform, and if this doesn't involve the Laplace Transform variable, I don't want to get very much. But it's an equation which I can easily solve. Okay. It's second order, so there will be two terms, right? I have, if you will, two independent solutions. And those solutions will have coefficients which are initially unknown, and I'll need two boundary conditions. One's at infinity, and initially I'm going to now be assumed that I'll throw away the term that blows up at infinity, because I don't like terms that blow up at infinity. And then the other boundary condition is on the body. So I have those two boundary conditions, so I'll determine my two coefficients, and away I go. And then I'll have an expression for phi, which depends, remember this is the Laplace transform, so it depends on P and Z, right? Okay, and I'll have that, and then I'll do the inversion by looking it up in a table initially. It will turn out, it will involve a Bessel function. Okay. I didn't say it's necessarily going to be sines and cosines, right? It will involve a Bessel function. But it will be known analytically. And it turns out the Bessel function goes to 1 if the frequency is 0. So it really is a simple form for steady flow. But it's a little more complicated for unsteady flow. But it gives you the first hint that things are going to get a little more complicated in unsteady flow. The corresponding functions that appear in subsonic flow, to the extent that solutions are known analytically, are Hankel functions, which are sort of cousins to Bessel functions. Right? So you'll get some fairly complicated functions, even in cases where you know the solution analytically. For three-dimensional flow, in supersonic flow, you will need a numerical procedure to determine the solution. So for 2D flow, we're going to have a nice analytical formula, which will be pleasant. And it'll be a little messier for unsteady flow than for steady flow, but it's known. In incompressible subsonic flow, there's an analytical solution in terms of these Hankel functions for the two-dimensional case, not for the three-dimensional case. So 2D incompressible flow has a more or less analytical solution due to Theodorsson, the famous Theodorsson. And the supersonic flow case, so many people worked on it, it's not quite clear who actually did it first. So it doesn't have a name associated with it. But once you go to 3D, it'll be a numerical procedure. And then in transonic flow, unless you're going to use Slender by theory for low aspect ratio winds, you're going to go to a nonlinear PDE, and that gets substantially more complicated. Okay, I'm going to stop right here today. What I'll do is look at the book. You'll see this equation written down. We're going to solve it. You'll see how it's solved, and I'm going to start here on Thursday. We'll solve it. We'll apply the boundary conditions. We'll do the inversion. I'll say a little bit about the inner workings of the inversion, because I think it's interesting physically. And And then once we have this, we will be able to go to 3D flow using a similar method. But you'll see that we can only go so far. We'll get a partial analytical solution, but then we'll have to complete it by a numerical procedure. Okay? Any questions before we depart for the day? Okay. Think transforms. Transforms are very useful. We're going to drive all this stuff using transforms. That's not the way it was done originally. I will spare you the agony of how it was done originally. But people use other methods. Okay, good.